Hello everybody and welcome to this Operations Research course video lecture, chapter 11 on data development analysis. And this will be a very short and concise, compact if you like, introduction to data development analysis. If you want to have a longer introduction and for example, understand this data development analysis in a graphical way, then I will refer to these old notes of this course that you can download here and chapter 6 there. But let's go to these notes. So this video lecture is about the Primal approach to data development analysis, and in the next lectures we have a so-called dual approach. And as has been the style in these lectures, I explain these things by using an example and not so much using theory. So let's have an example. So we have problem 11.1 here called Imperial Universities. So we have God Emperor Leto II who has decided to give a special imperial status to universities that are efficient. And there are 4 universities: University of Kaladan, Giedi Prime, X, and Kaitain. They have all applied this special imperial status. And to assess the efficiency, the imperial bureaucracy will consider certain kind of inputs and certain kind of outputs of these universities, and according to those, if the data supports it, then we calculate somehow the efficiencies of these universities. So the inputs, they are chosen to be Solaris, so the budget of the university, students, number of students they have, number of professors, and then the universities also use this famous spice melange. So how much spice melange is used by the university, consumed by the professors, I suppose. Then there are outputs. So there are 3 kind of outputs in the universities. So they output Suk doctors, mentats, so these are the students become Suk doctors or mentats, and then they also develop Ixian technology. And then the actual numbers, so the actual data of the problem is given here in the table. So here are DMUs, so these units that are assessed are called in this business DMUs. It's short for decision making unit. A funny name, but that's what it's used. So we have the DMUs are University of Kaladan, University of Giedi Prime, University of X, and University of Kaitain. And then the inputs and outputs are given here in these matrices. So the God Emperor decided to compare only the applicants to each other and give those that are 100% efficient the special imperial status. And now the question is which universities should be given this status. So this is solved by calculating their efficiencies by using data development analysis, or DEA. And to start with this problem, so let's consider what is the data here. So there are 2 matrices, the data. So here is the inputs and here are the outputs. So actually, let's call them matrices X and Y. So X is the input matrix that is here, or actually it will be this transpose. Y transpose, it just happened to be transpose. And Y will be the transpose of this. Sorry about this confusing way of writing sometimes rows and columns and then switching them around, but this happens often because, as you should know already by now, the choice of rows and columns is a bit arbitrary, and of course if you choose them the wrong way around, then you can just transpose the matrix to get the other way around. So now I collect the data as matrices X and Y that will be the transposes of these. So what do I mean? So the XIO again in this business, the sub-index O is usually used when we take one DMU and take it under consideration. So the O is, I don't actually know why it's called O, but now the O is just an index. So XIO will be the amount of input I for the DMU O, and YJO will be the amount of output J for the DMU O. So what does this mean? In the matrix X and Y, the data of problem 11.11 in the previous page, X is this and Y is this, and you should note, for example, X, the first row is 9, 8, 2, 27. Here is the first column. So these are transposed. There is nothing profound why they're transposed. It just happened to become this way. All right. So now that's the data of the problem. Then we should understand or calculate somehow the efficiency. And now this is a bit of a problem. So what does it mean that is an efficiency? So let's call theta. So the bold-faced theta is a vector for all these efficiencies, and then theta subscript O would be the efficiency of the DMU under consideration. And of course everybody knows what is the efficiency. It's output divided by input. Yes, that is the efficiency number. But now we have many outputs and many inputs. So how do we still calculate the efficiencies? And the first thing that usually comes to mind, which is traditional thing, is okay, so we weigh the inputs with some numbers and we weigh the outputs with some numbers and perform the ratio. So formally, or not even formally, it's just on the idea level, the theta, the efficiency, is that you take the weighted outputs of the DMU and divide it by the weighted inputs. Okay. So let us look at this for example, Caledon. So University of Caledon, it has the weights U1, U2, and U3 would be the weights or the outputs, and outputs are 9,500, 500, and 120. So these are the outputs. Caledon here. So it's this row or this column. So we're looking outputs Y. All right. There is a typo. It should be either there is a typo, this 12, or this is a typo. Let me check. 12 patents. So PATS means patents. So this many X-Tech patents. So that's a typo, this 120 here. That should be 12. And then we have to divide it by the weighted inputs. So what are the inputs? Inputs are the first column here with the X, like this, or the first row here, like this. So 9, 12,500, 1,303. And then there are the weights V1, V2, V3, and V4 for the inputs. And then what happens next, this is just, I've written this symbolically, this sum, and then finally I have written it by using a vector notation. So U is now a vector of U1, U2, and U3, and V is a vector V1, V2, V3, V4. Y bullet O. Bullet means that rows run free and the column O is fixed. Same here for X. Okay, that's well easily enough written. Of course, they are a little bit complicated, these formulas, but you should be used to these formulas already. But the problem is now, okay, once the weights are given, we just calculate the efficiency there. But how are the weights given? Who gives the weight? And you may think that maybe the emperor wants to give the weights. So fine, if the emperor gives the weights, then everything is calculated according to the weights, and we will check whether it's 100% efficient or not. But the emperor doesn't want to do this. He wants to compare these different DMUs, these different universities, to each others, and so the weights somehow are calculated by comparing all the DMUs together, and nobody just sets them. So how does this happen? And now comes the clever trick. So each DMU wants to look as good as possible. So each DMU wants to be 100% efficient. So then for the DMU, this would be a maximization problem of these weights. So the weights V for the inputs and weights U for the outputs. These are decision variables, so that the decision-making units, that is our universities, they want to fix the weights so that they look as good as possible. And this means they want to maximize their efficiency number theta. So each DMU O, so this is a maximization problem for each DMU, for each university. This is the old maximization problem, where they want to maximize this weighted outputs divided by weighted inputs. So this is what they want to maximize. Let me put this slightly bigger. So this is the problem. So now we already run into a hiccup. So we want to have linear problems, and this is a fractional optimization problem. So here's a decision variable U times something divided by V something, and UV, this pair, is our decision variables. And this is not a linear function of U and V. This is a fractional function. But now we have a neat trick that solves this problem. Since this is a fractional number, if I multiply, for example, here the upstairs by some number alpha and divide by the same number alpha, nothing changes. And if you think about it a little bit, this means that we can normalize this system so that we can always assume that this denominator here is 1. Because if it's something else, we just scale with that number and we get the same maximum, same number. So let us then because of this, maximizing this fraction, this divided by this, is the same as maximizing the upstairs nominator here, condition that the denominator is equal to 1. Again, the reason for this is that if I have some solution U, V, then alpha U and alpha V is the same solution. It gives the same number. I've just multiplied the numerator and denominator the same number, nothing changes. So I can assume that this downstairs here is a given number, any number basically. And why not take it to be 1, because that's simple. So I can maximizing this is the same as maximizing the upstairs, subject to the constraints that the downstairs equals 1. Okay. So we are arrived at this kind of maximization problem, and this is a linear problem. Of course, this is not a very good problem yet, because maximizing with this, well, take V whatever so that this is 1, and take U as big as you like, so this becomes bigger and bigger and bigger and bigger. So this is actually an unbounded problem. So there are not really constraints yet. And now comes the second clever trick, or this actually is the clever trick for this DA business. This trick here works for every fractional program. So whenever you have maximizing some rational function, so a function that is linear divided by another linear, you can always turn it as a linear optimization problem by constraining the denominator, the downstairs, to be 1. This you can do always. This is a general trick. So next we have a particular trick. So particular trick for the DEAs. And the thing is that, okay, the DMU under consideration can choose the weights in principle anyway they like, but then all the other DMUs are evaluated with the same weights, and we assume that the efficiency is never bigger than 100%. So this is when we end up with this kind of program or optimization problem. So we have the maximization of the output weights, weighted output, constraint subject to that the weighted inputs are 1. And then we have here, for example, we have the weighted outputs divided by weighted inputs for the DMU1, bullet 1. This should not exceed 100%, that is 1. The same for the DMU2, DMU4, and so on, and DMUN. So these constraints say that when maximizing the efficiency or finding the weights that maximize your efficiency for a DMU1 observation, then the same efficiency or the efficiency associated with those weights are calculated for all the other DMUs also, and they are not allowed to exceed 100. Alright, so this is basically the whole idea. Now there is a small problem that these are fractionals or fractions. They are not linear constraints, but it's easy to write them linear by just multiplying the downstairs, the denominator. So this fractional program, if you like, is this linear program. So here we, for example, this first one, we just first multiplied by these that are the input weights here. So it was then that this one is less than equal to this one, and then we put on the other side. So it's like this. So this is a linear program. It's written in a very, maybe a little bit confusing way, but believe me, it is a linear program. All the variables, this is the variables x is then u, v. Alright. So the objective in this linear program comes from the output matrix y, and the technology matrix is a combination of x and y. So this is certainly not a standard form LP, far from it, to be honest. But once we turn it into a standard form LP, we can solve it with the GLPK. And that's actually an exercise for you. Exercise 11.3 is called DALP. So consider this kind of very weird looking, if you maybe optimization problem. So you should formulate this as a standard form LP. So what does it mean? Find C, A, and B such that this problem 11.2 is a standard form LP where the decision variables x is this big vector where you first have u and then you have v. And how to do this? Do I give any hint? And there is a hint. The hint is actually in the solution of this. So we next solve this problem 11.1 by using GNU Octave, and if you look at the code carefully, there is a hint there on how to solve the problem 11.3. and the hint is on line 55 to 58. Alright, so let us then go to this solution and read this carefully so you get the hint for exercise 11.3. So as typical, we solve this problem 11.1 Imperial Universities by using GNU Octave and the GLPK. And here is listed the solution. It's also downloadable from my webpage. It's called impuni.m. And here is a script file. As always, we start with some kind of title block so that you can read what is this problem. Then we give the data of the problem. So the data is x and y. These are the inputs and outputs. So I've given them here. So here is x. And forget these. At this point here is y. I've also written here in the comments explanations of the marginal nodes. So this is the Caladan. This is Giedi Prime, this is X, this is Kaitain, and then Solaris students, Professor Spice. And notice that I have written this now in the same way that is in the table where I gave the problem here, and then I decided, for some reason that is completely not clear to me, but I decided to have this input matrix and output matrix with transposes of these, so the rows and columns were switched around. So that's why I have to put the transpose here. Note this transpose and this transpose. So that's the data, basically x and y. Then there are in this data section something else also. These are more or less shorthands. So NDMU is the columns of x, so how many columns x have, but the number of columns of x is the number of DMUs. Then I need ODMU, that's the zeros. So this is the, in this case, when the NDMU, so number of DMUs is 4, so this is just 4 zeros on a row or a column, I don't remember which way. N in is number of inputs, so that's the rows of x. O in is the zeros for the inputs. N out, rows of y, number of outputs. And O out is the zeros for each output. These are shorthand notations basically. And then we calculate the inefficiencies. So this is the block that does the actual work for the DEA. And okay, this is maybe slightly complicated what happens here, so let us go this block by block. So first I design the constraint type. So what is the constraint type? So first I have an S, meaning strict, meaning equality. So the first constraint is this. That's an equality, equals. Then I have constraint for each of the DMUs. So N or NDMU types times constraints that are upper bounds, U's. This is what happens here. So then I goes from 1 to number of DMUs, NDMU. Remember that this NDMU is the columns, number of columns of x, number of DMUs. And then I put the constraint type with the constraint type appended by U. So this, after this loop, the C type will be a string where I have first S for strict and then U for each of the DMUs. Alright, then we need a variable type, V type. So all of these variables are continuous. And how many do I have? I have U plus V, length of U plus length of V times constraints, sorry, variables. So I have for each output I have one variable, for each input I have one variables. So they are called u and v, but in this solution they have not given any name. So how many do I have them? Well, I have n out, number of output variables, but number of input variables. So j goes from 1 to, and note that there has to be parentheses, 1 to n out plus n in. So n in is the rows of x and n out is the rows of y. And then, so I'm beginning with an empty string, and then in this loop I append with c. So this, after this, v type will be a string of c's, that is n out plus n in, as that as a length. So these I think were relatively easy, not too complicated, but then there is something that is very complicated. So here in the for loop, so I start from O goes 1 to ndmu. So O is now the DMU under consideration. So I have ndmus there. So I have to solve ndmu different LPs. And in the loop we solve the LP number O. So what is the C? So this is not too difficult. So the C here is the output weights times the outputs. So the output weights, these are decision variables. So what is the C? Well, the C is basically we have this for output variables, and then we have to remember that our decision variables is outputs and inputs. So we then should have the coefficients for the inputs variables, but they don't appear in this maximization, so they are zeros. So this here defines the C, and the C here will be the oath row of output variables and transpose, so this would be the columns. Now I transpose it into rows. Then I have zeros for the input variables, and then finally single quote makes it a column vector. So this C here is, so this here is for the coefficients for the U, V, and these are the, other way around. So this here, the output weights for the O are this, and these are just appending right amount of zeros after it. That was relatively complicated. And wait, it gets better. The next one, and this is probably the most complicated thing we have had so much in so far in the course. So what is the matrix A? So first we have output variables, number of output variables zeros here. So this O out, this is 0, 0, 0, 0, 0 for all the output variables. Then I have the input weights for the oath column transposed, so this is a row again, and then note here is a semicolon. So after that, what we have here, we have a y transpose minus x transpose matrix. So this, and you notice there are these quotes everywhere, so I make transposes a lot. So what happens here? So this technology matrix. So first this one here, this looks rather fancy. That corresponds to this. So here we have first zeros, and then we have v, which will be the decision variables, times x bullet o. So the x oath column. This equals 1. This is the equals 1 is there in the b, but the left hand side is this. So again, this here is this here. And then the rest of the block, so this you have y minus x somehow, yes? This is what happens here. It so happens that we have to take transposes. If you write it out a little bit, you will notice that you have to take transposes. But this is something that if you don't check it yourself, it's probably you don't get it. So try writing this with small dimensions, really opening this matrix notation. Then you will notice that what you actually have, this block here, is that you have first matrix y transpose, then minus, so you have u minus u transpose, y transpose minus v transpose, x transpose will be this whole block here. Sorry, not these inequalities. So this block here is this block here. All right. Well, then the b, this is not difficult. B is 1 and then zeros for number ODMU, that was the zeros for each DMU. So b is 1 and then zeros. That's it. Then we just have to call the GLPK. We call GLPK CAB empty C type V type minus 1. This is a maximization. So this you should now, you have seen this many times, so you should understand what's going on here. Maybe a little bit of a trick here. So in principle, GLPK gives us two answers. It gives the optimal decision and the optimal value. Now the optimal decision will be the weights, and we are not interested in the weights as such. So the weights we assign to a temporary variable. We have to assign it somewhere. So let's just call it temp or whatever you want to call it. The main point here is that then theta will be the optimal efficiency, so the optimal, not decision, but optimal value. And then I will build a vector. So theta parenthesis at index O will be given the efficiency for the DMU O. And once this for loop goes around, it will produce the vector theta, where there is the efficiency for each of the DMUs. So then the final thing there is that we print out in the final block theta. So this will print out the efficiencies. Again, I don't demonstrate this with Octave. You have seen Octave demonstrations a lot. You should be able to do it yourself. I'll just show a little bit of output. So here is a test output. So you call test imp_uni just without .m, and then it will give you theta is 94%, 100%, 100%, 44%. So we read there that University Caledon is 94% efficient, University of Giedi Prime is 100% efficient, so is University of X, and University of Kaitain is 44% efficient. So Giedi Prime and X will get the special imperial status. So that was the solution of the Imperial Universities problem. Then there is one more exercise. So this is a kind of obvious exercise. So this was a rather painful thing to do. So it would be, of course, if you want to calculate many DEA problems, data development analysis problems, it would again be nice to have a program that does it automatically. And indeed, this is the exercise 11.5. So make a function DEA xy that takes the input matrix x and the output matrix y and then returns the efficiencies. And how to do this, what's a hint for this? Well, it is this imp_uni.m. So somehow you should make this happen automatically, and it's almost there. I think that if you look it carefully, there is not much to be done. So you just rewrite slightly differently what is written here. You don't even have to make too many changes. You will have this function. So that was the primal approach to data development analysis, and in the next lecture we have the dual approach. See you there. Bye.